Welcome to lesson 5, ladies and gents, of the weather and climate module. This one is all going to be about controls on a place's climate. We know that there are many different places all around the world, and each of them is going to experience different temperatures, different amounts of rainfall, and all those kinds of things. And we're going to try and sum up what we know about that for global scale, and then we're going to look at a smaller scale. So by the end of this video, you should understand that essentially every place has its own unique climate and that there is always a very good reason for that. Okay, I'm going to start global, which is revision of what we have talked about in the previous 4 videos. The most important control globally on a place's climate is its latitude. Now, lat is flat, or it's to do with how far north or south of the equator you are. The equator and the tropics are lines of latitude, and of course there are others as well. Why is that important? Well, we know that it's hotter at the equator than it is at the poles. We worked through 4 different explanations for that. Therefore, if a place is near the equator, it will be warmer than if it's closer to the poles. It's that straightforward. But we also know this tricellular model, this model of atmospheric circulation, with all these arrows going off in all sorts of different directions. We know that where arrows are rising, that's low pressure, and low pressure means cloud, precipitation and wind. Where the arrows are sinking, it means exactly the opposite. It means high pressure, no cloud, no precipitation, no wind. Therefore, where you are in relation to that model will have a profound effect on the climate of that place. If we take Brazil here, which is near the equator, it's going to be warm because it's near the equator, obviously, but it's also going to be wet because it's an area of low pressure, hence why we have the Amazon rainforest. If we take this part of the world, the Sahara Desert in northern Africa, we know it's going to be hot because it's near the equator, fine. It's also going to be about 30 degrees north of the equator, which is where we have arrows sinking towards the ground. It's high pressure. That's why the Sahara Desert is where it is. And I could keep going on, but you hopefully get the gist. And the more that you can get your head around high and low pressure, and the more that you can get your head around that model, the better you will understand how that affects things. That leads to what's called the Kopp Classification, K-O-P-P-E-N, the Kopp Classification, which will be in your module booklets. You can very simply divide the world into 5 climatic types, and you don't have to be too perfectionist about this. It's the broad ideas. If we look at the red colour is equatorial. It's low pressure, it's warm, it's rainy. It's where you find the world's rainforests. B is arid, it's dry, and that's because of high pressure. C is temperate. Doesn't get that hot, that cold, that wet, that dry. Temperate is sort of not extreme, it's in the middle. D is snow. We're getting further and further away from the equator, it's getting colder, so our precipitation is much more likely to fall as snow rather than rain. And then E is polar. You might be thinking, well, hang on a minute, Nikki, the Himalayas are not near the poles, I'm not stupid. Well, no, but let's think back to tectonics. They're very high up, which makes them very cold, and we're going to be picking up on that in a minute, but that is not a mistake. Look, you can see it here as well. So there is some relationship between mountains and this white colour, which we will pick up on another time. We can look at climate graphs to explain this as well. Look, so 23 degrees north, relatively near the equator, reasonably high temperatures. 57 degrees north, much nearer the poles, much lower temperatures. It's all the stuff that we've been learning about. If we're in the southern hemisphere, the pattern of temperature is opposite, isn't it? Because remember, the sun shines directly over the northern hemisphere in June, but in December the sun is then in the southern hemisphere. So we see this complete opposite pattern of when it's hot and when it's cooler. So play around with that, do a bit of Googling if you need to, but where you are in the world will have a profound influence on your climate because of how close you are to the equator for heat, and also where you are in relation to the tricellular model for the other things. But we need to work through smaller scale explanations, and the likelihood is that in your module booklet there will be a page of bullet points that we will pick up on. The year that I'm making this video, it's page 17. Okay, so as well as your latitude, the other thing that you would have to take into consideration when explaining a place's climate is its altitude, which is how high up it is. And I'm using Kilimanjaro as an example here. So Kilimanjaro is very near the equator, and yet you can very clearly see from the image on screen that it has snow and ice on the top. Clearly, its latitude does not explain that, but its altitude very definitely does. And once again, I've got an easy explanation and I've got a more complicated one, and you can sort of choose which one you go for. This is the one that I need everybody to learn, and it is written in the module booklet. We know from the first video that the higher up you go in the troposphere, the colder it gets. Well, today I can give you a number. It's 0.65 degrees per 100 metres, or you could say 6.5 degrees per kilometre. It's exactly the same rate, I'm just expressing it in two different ways. That's fine. It gets colder as you go up in the troposphere, and therefore it is possible to have snow and ice on mountains even if they're near the equator. It explains what we just said here about the Himalayas and the Andes and the Alps, etc., etc. It also explains Kilimanjaro. But if you are up for the challenge, the problem of that normal lapse rate is it is not about air that is moving. It's just about what happens with altitude. Now, mostly on the planet, air is moving around, so this one is not particularly realistic. And that brings us to adiabatic lapse rates. These are not crucial. If I explain these and you think, oh my God, I just know, stick with the first one. If you get these, fantastic. Right, first thing you have to do is you have to separate air into dry or moist. Most air has got water vapour in it, but some air is dry. I'm going to explain dry air first because it's easier, but it again is not massively realistic. Deserts, it may well be true, but most air has got some water vapour. If the air is moving, which remember is the fundamental difference between the environmental lapse rate and the adiabatic lapse rate, if the air is moving, it cools more quickly. So instead of 6.5 degrees per kilometre, it's 10 degrees per kilometre. It cools down and warms up more quickly. That's easy. But when you start to add water vapour into the equation, it starts to get a little bit complicated. I'm going to do a little bit of year one revision with you here. So it says, when air saturated with water vapour rises, some of the vapour will condense. It will change from being a gas into being a liquid. Because it changes state, it releases heat. When water changes from being a solid, a liquid or a gas, it will either use up heat or it will produce heat. And that is covered in year one water cycle. And maybe you want to pause the video at this point and go and revise that. But anyway, when water vapour turns into liquid, it releases heat. So let's think about this. The air is rising, it's cooling, but as it's cooling, it's also producing heat. That heat is going to counteract the cooling. Basically, it slows the cooling down. You do not learn any numbers for this because every percentage difference in moisture would have a completely different number, and we have not got the time, the brain capacity, or the will, I would say, to learn them. But the fundamental point is, if moving air is wet, it will cool more slowly because the latent heat being produced has a cancelling out effect on the cooling. Now, here's the interesting thing. If you start off with wet air and it rises and it cools, what you're going to have is the production of clouds, and those clouds are going to produce precipitation. Therefore, what the air is doing is it is drying out, because as it's rising and cooling, the water is turning into clouds and rain and snow. And that brings, ladies and gents, the rain shadow effect, which is really cool and worth knowing. Even if you don't fully understand why it happens, it is worth knowing what the rain shadow effect is. We start here then with wet air, moist air. The air rises and it cools. And as it cools, the water vapour turns into liquid, produces clouds, and you get rain. We call this relief rainfall. But all this time, what the air is doing is it's drying out. And then when the air sinks down the other side, it is dry. It has also warmed up. Ha-ha. Now that means that this side of hills or mountains would get completely different weather conditions to this side of hills and mountains. And it's called the rain shadow effect. It happens in the UK. It happens all over the world, actually. And if you want a nice simple diagram, it happens in South America. And this would be a really nice synoptic link for essays, because the Andes Mountains, of course, have been created by a convergent plate margin. So as the continental crust has been bashed into, it's folded and created these mountains. The mountains are only there because of tectonics. But now that they're there, you get the rain shadow effect. The air is forced to rise over the Andes, it cools, it produces clouds and precipitation, and by the time the air sinks the other side, there's no water left, and you get the Atacama Desert. And it hasn't rained for at least the last 400 years in the Atacama Desert. It is unbelievably dry. And it's all because of that effect. Okay, so altitude will affect your climate, how high up you are. That is your easy option. That is more complicated, but it would be worth everybody just having a basic understanding of the rain shadow effect. Right, gets easier, I promise. Proportion of land and sea. Right, first thing I can say, and I wouldn't blame you if you've never noticed this. If you look at a map of the world, here is the equator, look. If you find Lake Victoria, you can always figure out where the equator is. Have you ever noticed that north of that line there's more land than sea, and south of that line there's more sea than land? Oh, well, now you know. Why on earth is that important? Well, it's important because of this, something called specific heat capacity. If you're a biologist, you will know, well, I suppose, or a chemist, or a physicist actually. If you're a scientist, you will probably know everything about this. Specific heat capacity is about how much energy it takes to warm something up. And water has an incredibly high specific heat capacity. So we don't need to learn the numbers, okay, at all. I'm just using them to prove a point. It takes significantly more energy to heat up water than it does, for example, sound. Therefore, this is the bottom bullet point, is the only one that we need to know. Water takes longer to heat up and longer to cool down. So, summer in the northern hemisphere is hotter because there's more land. Land heats up quickly, it cools down quickly. Sea takes ages to heat up and ages to cool down. So there is a variation in temperature between the northern and southern hemisphere. Okay, but actually we are much more interested in this effect, the coastal / inland issues, because it's exactly the same point. If you live on the coast, you live near the sea, obviously. We've just said that water has a very high specific heat capacity. So what that means is that the coastal areas are going to be regulated, if you like, by that issue. In the summer, coastal areas don't quite get as hot, and in the winter they don't get as cold, because the sea is always a few steps behind where the land is. You'll know this if you go open water swimming, if you go swimming in the sea. March is just about the coldest that it's going to be, because of course the whole of the winter the sea has been cooling down, and by the time you get to March it is really quite freezing. Whereas if you go in the water in sort of September or even early October, it's not that bad, because it's still got the heat from the summer. So whether you are coastal or inland, whether you're northern or southern hemisphere, the sea and coastal areas are different to inland places. Okay, number 3. We'll pick up on this a lot more when we do the UK climate, but all you need to say for this one is wind direction in a country, or in a place, I should say, is really important, because the wind will bring the characteristics of where it's come from. If it's come from a cold place, it will be cold. The media nickname this one the beast from the east, and that brings some of our coldest weather because it comes from Siberia. Fairly obvious. If the wind comes from northern Africa, it's lovely, it's really warm, it's our kind of heat wave kind of conditions. If the air comes from the Arctic, it's going to be cold. Wind direction will have an effect on your temperature. Also, if the wind has come from land, continental, it's not going to have a lot of water vapour in it. If it's come from the sea, it's going to be full of water vapour. Therefore, it will also have an effect on how much precipitation you receive. So we've got altitude, land and sea differences, air, aspect. I love this photo. I didn't take it, which is sad, but I love it. Aspect is about which direction something faces in. And the most likely place that you will have heard about this, if you do environmental science, you'll hear about it there. But for everybody else, it will be to do with house prices. When people are looking at houses, particularly in the UK, people are obsessed with which direction the garden faces. Is it a south-facing garden? If you think of where we are globally, and I'm just going to go back to that map, okay, so here's the UK. We know that the sun will only shine directly in the tropics, the intertropical convergence zone. So the furthest north the sun directly shines over is the Tropic of Cancer. The sun, therefore, is always south of the UK. This side of the valley is looking at the North Pole. It's a north-facing slope. This side of the valley is looking at the equator. Because the sun is always south of the UK, this side gets direct sunlight. It's warmer, it's better for farming. It would make a nicer garden for sitting in the sunshine and growing lots of plants. This is a north-facing slope. Look how much colder that is. The morning frost hasn't melted. Because it's looking at the North Pole, it never gets direct sunlight. It's much colder. You wouldn't find it as easy to farm, you wouldn't find it as easy to grow plants, it wouldn't be such a nice garden for a house. So aspect is all about which direction something faces, and in the northern hemisphere you want south facing because it's much warmer. Okay, nearly there, I promise. Clouds. Okay, clouds are good and bad. And I'm not even talking here about precipitation. Obviously, if you have clouds, the chances it's going to rain or snow. If you don't have clouds, it's not going to. But I'm actually much more interested here in temperature. On a cloudy day, the clouds will block insolation. Insolation is covered in the first video. Insolation is heat from the sun. So on a cloudy day, the problem you have is that a lot of that insolation is going to be blocked by the cloud, and therefore it's not going to be very warm at ground level. If you don't have any clouds in the sky, you are going to get maximum insolation and you're going to have a really hot day. However, the reason that there are photographs of beds, which you've probably been wondering about, and I can't say I blame you, it's the duvet or lack of the duvet. Clouds perform a very different function with temperature at night time. If you have a duvet on your bed, what it does is it keeps you nice and toasty warm overnight so you can get a good night's sleep. It keeps the heat in, which is exactly, ladies and gents, what clouds do. They trap the heat. If you don't have clouds in the sky at night time, it would be like not having any bed sheets or duvets or anything on your bed. All of the heat would be lost overnight, and by morning you would be freezing cold. And what that means essentially is that deserts, which are high pressure areas, have extreme differences in temperature. They don't have any clouds during the day, so you get maximum heat and might reach 50 degrees. But at night time, there's no cloud to keep that heat in, and you may well get less, you may well go below freezing. Extreme temperature differences. And of course, because of the lack of cloud, they hardly have any rain. Whereas if you lived in a low pressure area, your difference between day and nighttime temperatures is not going to be that great. Sorry about the noise. So clouds, yes, obviously, they have an impact on precipitation, but they also have an impact on temperature. Okay, last one, nearly there. We are going to pick up on this much later in the module, but all I'm going to say for today is the climate of an urban area is often very different to the climate of the countryside next door, for reasons that I will fully explain in another video at another time. But that's it, well done. That's a pretty lengthy video. Good luck with it, folks.